We're constantly facing these simple yes or no questions in life. But what if the answer isn't just a flip of a coin? That's where logistic regression comes in. And here's the cool part. It's not just about predicting what will happen. It's about understanding the why, the actual probability behind that prediction. So that's exactly what we're going to unpack today. I mean, really think about it. Is a customer going to stick around or leave? Is this email spam or is it legit? These are the kinds of yes or no questions that organizations are wrestling with every single day. Logistic regression is tailor-made for this stuff, and how it gets to the answer, well, it's pretty darn clever. Okay, so if you've been around data at all, you've probably heard of linear regression, right? It's fantastic for predicting things that can keep on going up, like the price of a house. But when we're dealing with a yes or a no, we're in a totally different ballpark. We're not predicting some value on a scale, we're predicting a chance, a probability, and that requires a completely different playbook. So you might be thinking, okay, but why not just use a simple straight line? Seems easy enough. And you're right, it seems easy. The problem is when you're working with probabilities, a straight line can go haywire and give you some truly bizarre, nonsensical answers. Yeah, there are two huge problems here. First, a straight line just keeps going. It has no boundaries, so it could totally predict a 120% chance of rain or a negative 10% chance that someone will click buy, which, makes absolutely no sense. Probabilities have to live between 0 and 100%. And second, let's be real. The relationship between all our data points and a simple yes or no is almost never a clean straight line in the real world. It's just more complicated than that. So if a straight line is out, what do we use instead? Well, we need a curve that's actually built for the job, one that understands probability. And that is where the hero of our story comes in, the sigmoid function, with its classic, elegant S shape. The sigmoid function is the absolute key to making this whole thing work. Think of it like a probability converter. You can throw any number at it, big, small, positive, negative, doesn't matter. And it will always give you back a value between 0 and 1. It perfectly squishes everything into that probability range we need. And here it is, the formula itself. Now listen, don't get hung up on the math here, seriously. The important thing isn't memorizing the equation. It's just knowing what it does. It takes an input, which we're calling z, that's based on all our data, and it transforms it into that nice, neat probability between 0 and 1. This little equation is basically the engine driving this whole thing. All right, so to really understand what's going on under the hood, we need to learn how to speak the model's native language. See, it doesn't really think in percentages like you and I do. It thinks in terms of odds, and even more specifically, something called log odds. Let's break this down. We start with something we all get, probability. Let's say a 75% chance of something happening. We can also express that as odds, right? In this case, it's 3 to 1. Now here's the trick. The model takes the natural logarithm of those odds. It sounds a little weird, but this is the magic step. It transforms everything onto a straight, linear scale, which means the model can now do simple, linear regression-style math behind the scenes. It's how it connects a simple line to that beautiful S-curve we saw earlier. And this brings us to the most powerful part of logistic regression. We can actually interpret what it's doing. The numbers the model learns, its coefficients, tell us how the log odds change. And if we do one more little bit of math, we exponentiate that coefficient, we get something called an odds ratio. This tells us exactly how much the odds of something happening change for every single unit increase in a factor, like age. That is a massive, massive insight. Okay, all this theory is great, but let's see how this actually works in the real world, where the stakes are high. Imagine a doctor using a model to figure out a patient's risk of heart disease. In a situation like that, a simple yes or no just isn't enough, right? The degree of risk is everything. So here's our patient, they're 60 years old, and their cholesterol is a 200. We're going to take these two numbers and feed them into a logistic regression model that's already been trained. The whole goal here is to get a clear, understandable probability of their risk. So, behind the scenes, The model takes the coefficients it learned during training, multiplies them by the patient's data, their age and cholesterol, and then adds it all up. This whole calculation gives us that final log odds value we talked about, and for this specific patient, that value comes out to exactly 1.
And here is where the magic happens. The model takes that log odds value of 1, pushes it through our friendly sigmoid function, and out pops our final answer, 0.73. In other words, this patient has a 73% probability of heart disease. See, it's so much more than a yes or a no. It's a specific, concrete, actionable risk assessment.
So it's pretty clear that this is an incredibly powerful tool. But, and this is a big but, it is not a crystal ball. Logistic regression has amazing strengths, but it also has its limits and some important assumptions that we just have to keep in mind. Really, it all boils down to a trade-off. On one hand, its biggest benefit by far is interpretability. We can actually look inside and understand why the model is making the predictions it's making. It gives us a real number we can use to make decisions. But all of that is built on a few key assumptions, like that the relationship is linear in that weird log odds space. If we ignore those limitations, our results just won't be trustworthy. And this really leads us to the most crucial takeaway of all. A model can give us a number. It can tell a doctor, hey, there's a 73% risk here, but it can never, ever tell that doctor what to do about it. Logistic regression is a phenomenal tool for quantifying uncertainty, but the final decision, how to act on that information, that is and always should be human. Thanks for digging into this with me.